All right, so the function, is it x e to the negative x? All right, so maybe the first thing you do is you take a look at what it looks like. And I'm going to start with a zoom decimal. All right, and so I got a function that looks like it's increasing. It maybe has a maximum, and then it starts to decrease. And I think it looks like it's going from concave up to concave down to concave up again. So like it's been, sorry, I said that wrong. Concave down to concave up, maybe. It's hard to tell. Do you agree? But maybe calculus will let me see that. Let's see. I think because we're recording, I'm going to recap and just say, don't forget about the perils of the second derivative test. This is a great perils of the second derivative test. And the moral here is that when the second derivative test equals 0, it tells us nothing. It doesn't tell us that it's not a min or it's not a max. It just tells us nothing, and it means you have to go back to the first derivative test. Okay? And that's why some people actually like the first derivative test, because it always works. It might involve plugging more things in to more intervals, but it always is going to tell you whether there's a change in increasing or decreasing, whether it's a min or a max. The second derivative test is a little more, you just find the next derivative and plug it in. So it's not as much plugging in, but it doesn't always work. All right, so let's see. We have x times e to the negative x. Part A, I think we just need the first and second derivative. A little tougher. Who's up? Morgan? Is that a hand or you? No, okay, go ahead.
Would it be negative x squared?
No way. Alicia?
X
For
e to the negative x times negative 1
first times the derivative of the second.
plus e to the negative x times 1.
Okay, second times the derivative of the first. I think you were trying to bring x out in front or something. All right, so it's Tuesday morning. Like, got to shake out the cobwebs a little bit. All right, so I'm actually going to, let's see. I'm going to factor out an e to the negative x, and I'm going to be left with negative x plus 1. Is that okay? And I think I might actually even rewrite it as e to the negative x, 1 minus x. And I actually, I'm going to tell you that simplifying it a little bit now is going to make a lot of our calculations later easier. And I think I said this all along last chapter. There's going to come a point in time where actually simplifying it a little bit might make it a little easier. All right, Alicia, find someone to do the second derivative. Do you want to?
Okay, fine.
All right, good.
Okay, so I do it kind of differently.
Okay.
E to the negative x times negative 1.
All right, first times the derivative of the second. We're good.
Okay. Plus e to the negative x. Or, negative
Okay, I'm going to put the negative 1 here, so the derivative of the first
times 1 minus x.
times the second. Okay? I would say the same thing. I'd factor out an e to the negative x, and I'd be left with negative 1 minus 1 minus x. How'd I do for my algebra? Is it all right? Let's see. Negative 1 minus 1 plus x. So David says that's the same as negative 2 plus x, or x minus 2. Did I do all right simplifying? I get nervous. So, no, I'm serious. I do, because if I do it wrong, then the whole problem's wrong. See what has that thought occurred to you yet? Like, if you take the derivative wrong, like, everything else goes wrong. It's bad. That's why you need to be a qualified differentiator. You need to be awesome at that. Okay?
Why is it called differentiation?
Because you're taking the derivative. What do you want to call it? Derivatizing?
No.
I really like it. Yeah.
Great. Thanks, Morgan. That's awesome. Raise your hand next year in college, please, and say, yeah, my teacher told me it was derivatizing. Ah, great.
I don't know about you, but I'll say that.
All right, so I need to find the critical points. Kelly, critical points, where do they happen?
At X.
No, I didn't mean exactly where. I just meant where in general do they occur? At two places. Either
When the derivative equals 0. Okay.
or,
Or I don't know.
no, undefined. When the first derivative is 0 or undefined. That's important. Okay? Now, it just so happens that there are no values for x that you can plug in that will make this undefined.
What about imaginary numbers?
So, you can actually, after you take calculus, there's complex calculus, and it doesn't mean it's harder, it just means that you do it in the imaginary plane. So, that's to come. But for all intents and purposes, pre-calc and calc have been dealing almost exclusively with the real numbers, real number system. All right, so we need to know, when is this equal to 0? Well, I don't think so.
At when x equals 1.
I agree when x equals 1. What's e to the 0? 1. As a matter of fact, e raised to something,
Never be 0.
it's never 0. As a matter of fact, e raised to something is always going to be, yeah, what kind of number? I think so. E raised to anything is always going to be a positive number. Always. So e to something is going to be positive. So e to the negative x is never going to be 0, and 1 minus x, if x equals 1, that's going to be a critical point. Yep. So we now have to look and see, all right, that's a critical point. Is it a minimum or maximum? All right, you have a couple choices, and I'm willing to do whatever you want to do. Do you want to do the first derivative test or the second derivative test? Okay. See, I told you, some people have different, so you're already leaning towards the first derivative test. Now, you know we're going to have to take the second derivative anyhow, right? Yeah, okay. All right, so here's the first derivative test. We need to make our number line, and we only have one critical point, which is at 1. And we know that the derivative at that critical point is 0, and so that divides my function up into two zones, right? Familiar from like 2 chapters ago when we looked at the different zones. So I have to ask myself, what's the derivative doing on each zone? And so I have to pick some sample points. I need a number less than 1. 0 is a great one to pick. All right, let's plug it into the derivative. E to the 0 is 1. 1 minus 0, so 1 times 1? 1. More importantly, it's positive. You guys are good at this. I feel like we're in a classroom in like the 50s or something. 1, positive, and you're all saying it in unison. It's very nice. All right, so the function, increasing. All right, something bigger than 1. All right, I was thinking like, all right, fine. I was thinking 1,000,000, but 2 is fine. E, yeah, I don't know. E raised to anything, I don't care if it's to the 2, it's positive, because think about it. E to the negative 2 is really 1 over e squared. E squared's positive, 1 over it's going to be positive. And 1 minus 2 is negative times a positive? Negative. So this is decreasing. And let's see, increasing to decreasing, that has to be a max. And here's what you're going to have to write if you get a min or a max. And and I won't give you credit on your homework tomorrow. I'll say you didn't do your homework unless you write it. Since the derivative goes from positive to negative at x equals 0, there must be a maximum at x equals 0. So I'm going to look for those sentences.
That is the most annoying thing I've ever
I know.
heard.
X equals 0 or X equals 1?
Yeah, is that what I want to say? Thanks. Katie says, you've got this all backwards, Mr. B. You're absolutely right. It's x equals 1, right? Oh, gosh. All right. Good place to stop and ask a question. How's that? Is that all right? And what you're probably going to do is you're probably going to end up going back to your calculator and doing like, is that right? Let's do second calc. Let's do max. And let's ask our calculator for a maximum between 0 and 2. And let's guess. It doesn't matter where. I thought I hit enter. Didn't I hit enter?
You don't have to do that.
Right. Hey, look. The calculator tells me there's a maximum at 1.00000023. Who's right? Who's right? The calculator or us? Us is right. Who's right? Who's right? The calculator or we?
Yeah.
Us.
Who is right? The calculator or we?
Us.
We are.
We are right. All right. We're right. The calculator's wrong. The calculator has some sort of algorithm that the folks at TI programmed that approximates where that maximum is. We got the exact maximum. As a matter of fact, just so you understand, if we wanted to actually say what the maximum was, you'd have to take 1 and plug it into the function, right? So x e to the negative x. So if we wanted to find out what the maximum is, the maximum occurs at 1 comma what? X e to the negative x. So that's, David says, 1 times e to the negative 1, which is 1 over e. So the maximum occurs at 1 comma 1 over e. Going back to your calculator, how many people actually knew that 0.3678 was 1 over e? Anyone? Oh, stop it. No. I mean, come on. You're never going to know that from the calculator. But if you go and you do 1 divided by e, sure enough, that's what it is, right? So that's the difference between being like an engineer who wants the decimal approximation and being the mathematician who can tell you the maximum occurs at 1 and the maximum is 1 over e.
Who the heck came up with E?
Euler.
What is it?
Euler, it's a number. It's like a constant, right? Just like pi,
Constant for what?
continual growth, right? It's the limit of continuous growth. Like you could compound once every day, minute, second, and every instant. If you compound every instant, your base is E. If you actually think about this problem, right, you did this last year, I think. Remember if we did like the rate over 12 and you'd raise it to the 12 to find the interest for the year?
Yeah.
Right? If it was like 5% annual, you divide by 12 and raise to the 12. If you took, 365 and raise to the 365, right? If you take 1 plus 1 over x raised to the x, right, and you look at the limit as x goes to infinity, I think that's your I'm pretty sure that's your definition of E.
Oh.
Okay, so I think I'm pretty sure. That's where it comes from. Alright, so 1 over e. So, we're ready to do the second derivative. I'm ready. Are you ready? Okay. Now, the second derivative we said was e to the x times x to the negative 2. Alright, so I need to find out where that's equal to 0. Alright. What can you tell me about e to the negative x?
Never going to equal 0.
It's never going to equal to 0. So x minus 2, what's that give me? X equals 2? Okay, so that's another place that something might be going on. As a matter of fact, the second derivative of 0 there, what might be going on at x equals 2? Inflection point of inflection. So maybe, we can't tell just because the second derivative is 0 there. We actually have to test it. So let's see. Yep. And this divides it into 2 zones, and I have to check a little bit above, a little bit below. What do you want to check less than 2? All right, e to the 0, 0 minus 2, so is that negative? Concave down. Something bigger than 2? All right, e to the million. Oh, sorry, e to the negative million. Positive, I don't care what it is. Actually, it's a tiny number, but it's positive. A million minus 2? Positive. Concave up. All right, so since there's a change in concavity, x equals 2 is a point of inflection. Or, since the second derivative goes from negative to positive at x equals 2, there's a point of inflection at x equals 2. Whoops. And you really need to see that change in concavity. You need to see the concavity change to say there's a point of inflection. And you need to write that sentence. You need to take that sign chart and put it into a sentence. True.
Is there a way to go straight from the function to the second derivative?
Tell me what you mean.
Like, rather than, we've never had a situation yet where, like, we needed to do the second derivative without needing to do the first. But if we were to do that, is there a way to just go, like,
do you mean to physically just take the derivative, the second derivative without taking the first derivative?
Yeah.
No, so the second derivative is the derivative of the derivative, so you need the derivative to reference to get the second derivative. There are probably some really clever people who can do parts of the derivative in their head so they don't need to physically write it, but you need to know what that is. All right, so we have a point of inflection at 2, which actually, if you go back to the graph, it looks like maybe there is something going on there. We're going from concave down to concave up at that x equals 2. All right, now.
What's the second derivative test?
All right, now the second derivative test has nothing to do with the point of inflection. The second derivative test is a test to see if it's a minimum or a maximum. If you wanted to...
You mix up first derivatives.
Wait, what?
You were saying second derivative is for min or max.
Sorry. Second derivative has nothing to do with mins or max. Sorry. The second derivative test has nothing to do with points of inflection. The second derivative will help us find points of inflection. The second derivative test is to see if something's a minimum or a maximum. You can use it in conjunction or instead of the first derivative test. So the second derivative helps us find points of inflection. The second derivative test helps us see whether it's a minimum or a maximum. So we knew that we had a critical point at x equals 1. If we take that critical point and plug it into the second derivative, let's see, the second derivative at 1 is going to be e to the negative 1 times 1 minus 2. E to the negative 1 is, positive. 1 minus 2 is positive times a negative. So this tells me that the critical point, if I plug it into the second derivative, would be negative. What does a negative second derivative tell us about the function? Concave down. If it's concave down at the critical point, it has to be a maximum. Okay? So the second derivative, instead of doing the first derivative test, the second derivative can also tell us if it's a minimum or a maximum. The problem, though, is that the second derivative is 0. It tells us nothing. It fails.
So it works for everything, unless it equals 0.
Right. If the second derivative is negative, it tells you that critical point's a maximum. If the second derivative is positive at that critical point, it tells you it's a minimum. And some people like that. Some people are like, well, that was a lot easier than plugging numbers into the sign chart. But when the second derivative tells you it's 0, it fails. It doesn't work. The test is not valid. Now, with that said, David, you still have to say now, since x equals 1 is a critical point, and the second derivative at x equals 1 is negative, then there's a maximum at x equals 1. So you still have to, it doesn't get you out of writing your sentence, right? Sam?
So are you saying that if the critical point is at x equals 0, that's when it fails? Or...
If you plug the critical point in to the second derivative, and it equals 0, it means that the second derivative test didn't work. And it means you have to go back to the first derivative test. Okay. Anything else? All right. So we still have a whole host of interesting functions to look at, like 3 and 4. Oh, I know what I wanted to tell you. On one of your homework problems tonight, they actually give you that's not what I wanted. They actually give you a sign chart. And I think they give it to you like this. They give you like a first derivative sign chart and a second derivative sign chart, and they like have x1 and x2 and x3, and they tell you like the first derivative is greater than 0, the first derivative is less than 0, the second derivative is greater than 0, the second derivative is less than 0, the second derivative is greater than 0. And they're asking you to look at this whole thing sort of divided up into all these zones. And it's a little bit confusing to look at. But the important thing to focus on is look at the first number line to see if the function is increasing or decreasing, and look at the second number line to see if the function is concave up or concave down, and then put those clues together. What reminded me of that was on the classwork, which we didn't do today, which maybe we'll do tomorrow. I give it to you in a table, and we've actually done problems like this before, right? 1 or 2 problems, I think, on homeworks or in class, and it's a little more organized when it's in a table. I like the concept of this type of question, like what can you tell me just knowing the sign of the first and second derivative, and that's why I assigned the question in the book. The book doesn't use a table, it uses like the number lines, which makes it just a little harder to look at, but same concept. All right. All right. I think we're good. More practice tonight, and I want to see those sentences tomorrow. No excuses. And if you didn't get 9 and 16,